In the grand silent theatre of the cosmos, a story is unfolding. It is a drama written in the language of starlight and gravity, played out across billions of years and unimaginable distances. The protagonists are the galaxy's colossal islands of suns, drifting through the profound darkness like luminous dust motes. For generations, we believed we understood the plot's main theme. We thought it was a tale of gravity, a cosmic epic of attraction. An initial explosive beginning, the Big Bang flung everything apart. Since that first incandescent moment, gravity, the universe's great director, has been working tirelessly to pull it all back together. The expansion, we were certain, must be slowing down. The only question was its ultimate fate. Would gravity win, pulling all matter back into a fiery big crunch? Or would the expansion continue forever, slowing but never stopping, leaving a cold, dark and empty universe in its wake? In the final years of the 20th century, two teams of astronomers set out to write the final act of this cosmic play. They sought to measure this deceleration to finally determine our destiny. Using the world's most powerful telescopes, they gazed into the deep past, hunting for ancient exploding stars at the very edge of visibility. These stellar cataclysms, type Ia supernovae, are fantastically reliable. They blaze with a known uniform brightness, making them perfect standard candles for measuring the vast distances of space. By comparing a supernova's apparent faintness with its known intrinsic brilliance, astronomers could calculate its distance. By measuring its redshift, the stretching of its light by expanding space, they could determine how fast it was speeding away from us. Putting the two together would reveal the history of cosmic expansion. Night after lonely night, in observatories perched on remote mountaintops, they collected faint photons that had traveled for billions of years. The data trickled in a message in a bottle from a younger cosmos. As they plotted their points on a graph, a strange and impossible picture began to emerge. The ancient supernovae, the most distant ones, were dimmer than they should have been. They were farther away than all our theories predicted. This could only mean one thing, a conclusion so radical, so profoundly unsettling that the scientists who discovered it thought they had made a mistake. The expansion of the universe was not slowing down. It wasn't even coasting at a steady speed. The expansion of the cosmos is accelerating. Some unseen repulsive force is at work on a cosmic scale, pushing the galaxies apart faster and faster with each passing moment. It is an anti-gravity, a phantom energy woven into the very fabric of space-time itself. We have given this enigma a name, though naming it does not grant us understanding. We call it dark energy. It is the most dominant force in the universe, making up nearly 70% of the total energy content of the cosmos. And its existence confronts us with the single greatest puzzle in the history of science, a discrepancy so monumental it threatens to shatter our most fundamental understanding of reality. The problem isn't that dark energy exists. The problem is that, according to our best theories, it should be catastrophically more powerful. Not a little more powerful. Not 1,000 times or 1,000,000,000 times more powerful. The problem is that our calculations predict a dark energy that is 120 orders of magnitude stronger than what we observe. That number is a 1 followed by 120 zeros. It is a figure more vast than all the atoms in the known universe. It represents the largest, most embarrassing mismatch between theory and observation in the entire chronicle of human inquiry. This is the story of that impossible number. It is the search for why the most powerful force in the universe is for some inexplicable reason almost perfectly turned off. Why is the cosmic accelerator set to a gentle whisper when it should be a universe-destroying roar? To begin to untangle this profound conundrum, we must travel back in time, not to the discovery of dark energy, but to its conception. We return to the early 20th century, to the mind of Albert Einstein. His newly forged theory of general relativity had redrawn our picture of the cosmos. Space and time were no longer a static stage upon which events unfolded. They were a dynamic, interwoven fabric space-time that could be bent, warped, and curved by the presence of matter and energy. Gravity was no longer a mysterious force acting at a distance. It was the curvature of space-time itself. But Einstein's beautiful equations held a troubling implication. They predicted a universe that could not stand still. The mutual gravitational attraction of all the matter within it should cause the entire cosmos to collapse under its own weight. This idea offended the prevailing wisdom of the time, and even Einstein's own intuition, which held that the universe was eternal, static, and unchanging. To salvage his vision of a stable cosmos, he introduced a modification. He added a new term to his equations, a mathematical fudge factor he called the cosmological constant, represented by the Greek letter lambda. It acted as a form of cosmic repulsion, an intrinsic energy of space itself that would perfectly counteract gravity's pull, holding the universe in a delicate static balance. It was a mathematical patch, an ad hoc solution to a perceived problem. Then a decade later, the astronomer Edwin Hubble made a landmark discovery. Observing distant galaxies, he saw that their light was uniformly stretched or redshifted. He realized he was witnessing the expansion of the universe itself. Einstein's original equations had been right all along. The universe was not static. The need for his cosmological constant vanished. Einstein famously would later refer to its invention as his biggest blunder. He had missed the chance to predict the expansion of the cosmos, one of the greatest discoveries in human history, because he had tinkered with his own work. For 70 years, the cosmological constant was a ghost, a footnote in the history of physics. Then, in 1998, with the discovery of cosmic acceleration, the ghost returned. Einstein's blunder was suddenly resurrected as a profound prophecy. His lambda, the intrinsic energy of space, was the perfect candidate for dark energy. The greatest minds in physics had a ready-made explanation for the cosmic push. There was just one terrifying problem. They already knew how to calculate it from first principles. And that is where the story turns from a beautiful vindication to a horrifying paradox. The stage for this new act of the cosmic drama shifts from the immense scales of galaxies and superclusters down to the impossibly small frothing realm of quantum mechanics. According to quantum field theory, the modern language we use to describe the subatomic world, a vacuum is not empty. Empty space is a misnomer, a classical illusion of tranquility. At the most fundamental level, the vacuum of space is a roiling, chaotic sea of activity. It is a place where pairs of virtual particles, an electron and its antimatter, twin a positron. A quark and an antiquark spontaneously erupt into existence from nothing, survive for the briefest of moments, and then annihilate one another, vanishing back into the void from which they came. This quantum foam, this ceaseless fizz of creation and destruction, is not a theoretical fantasy. Its effects are real and measurable. It subtly alters the energy levels of atoms and tugs on tiny metal plates in a laboratory, an effect known as the Casimir force. This seething quantum cauldron, by its very nature, must possess energy. This is the vacuum energy. According to Einstein's general relativity, all energy gravitates. All energy warps the fabric of space-time. Therefore, the energy of this quantum vacuum should act precisely like Einstein's cosmological constant. It should be the source of dark energy. So physicists set out to perform what should have been a triumphant calculation. They would use the well-tested laws of quantum mechanics to predict the energy of the vacuum, and that number should match the value of dark energy observed by astronomers. It would be the ultimate unification of the very large and the very small. Imagine the vacuum of space as a perfectly still, boundless ocean on a windless day. From a great height, its surface appears glassy, placid, representing zero energy. This is the classical view of the void. Now let's zoom in closer and closer with a microscope of impossible power. As we approach the surface, we see it is not calm at all. The water is in a constant state of agitation. Tiny ripples and waves, bubbles and troughs are forming and disappearing everywhere in a fraction of a second. This is the quantum view. These fleeting disturbances are the virtual particles. Each tiny ripple, however brief its existence, contributes a small amount of energy to the whole. To calculate the total energy of the vacuum, physicists had to add up the energy of all these possible quantum fluctuations, all these tiny ripples on the ocean of reality. The calculation involves summing up the contributions from all possible wavelengths, from the very long to the infinitesimally short. Physics tells us there should be a shortest possible wavelength, a fundamental limit to the resolution of reality known as the Planck length. It is the scale at which our concepts of space and time break down, where the smoothness of space-time gives way to a quantum graininess. So the physicists performed the sum, adding up the energy of all the virtual particles down to this ultimate cutoff point, the Planck scale. The number that emerged from their equations was not merely wrong. It was nonsensical. It was ludicrous. It was a catastrophe. The theoretical value for the vacuum energy density was a 1 followed by 120 zeros. The observed value, the gentle push measured by astronomers, is about 1. Let us try to grasp the enormity of this failure. This is not like predicting it will rain and seeing a sunny day. It is like predicting a gentle spring shower and witnessing the planet Jupiter materializing in your living room. Imagine you are building a house. You hire 2 separate surveyors. One uses satellite GPS to measure the foundation from space. The other uses a laser tape measure on the ground. The satellite surveyor reports the foundation is 10 meters long. The ground surveyor reports the foundation is longer than the diameter of the known universe. That is the scale of this discrepancy. It is the worst prediction in the history of physics. If the dark energy really had this theoretically predicted strength, the consequences would have been immediate and absolute. The universe would have been ripped apart by this ferocious repulsive force in the first 10 to the minus 43 seconds of its existence. Space-time would have expanded so violently, so instantaneously, that not even a single proton or neutron could have formed. There would be no atoms, no stars, no galaxies, no planets, and no life. The very possibility of structure of complexity would have been obliterated before it ever had a chance to begin. So the deep mystery is not, why is there dark energy? The true soul-shaking mystery is, why is there so little? Why is it so breathtakingly, unnaturally weak? It's as if we have discovered a cosmic bomb of unimaginable power capable of annihilating reality itself, but its fuse has been dampened by a factor of 1 with 120 zeros. The universe seems to be balanced on a knife edge of cosmic proportions. For life to exist, the value of the cosmological constant had to be tiny. If it were much larger and positive, the universe would have flown apart. If it were much larger and negative, the universe would have immediately collapsed. Somehow, 2 enormous numbers, the raw predicted vacuum energy and some other unknown cosmic factor, seem to have cancelled each other out with an accuracy of 1 part in 10 to the 120. It is like measuring the entire coastline of North America down to the individual grains of sand and finding that its length is precisely 0 to within the width of a single atom. This is the cosmological constant problem, or the fine-tuning problem. It represents a chasm, a gaping wound in the heart of modern physics. It tells us that our two great pillars of understanding general relativity and quantum mechanics are fundamentally incompatible when brought together. Something profound about our understanding of reality is deeply wrong. In the face of such a colossal failure, where do we turn? Physicists undaunted have proposed a gallery of exotic and beautiful solutions, each one pushing the boundaries of our imagination. One of the most elegant ideas comes from the search for a deeper form of symmetry in nature. Symmetry is a guiding principle in physics. It brings a sense of order and predictability to the laws of the universe. For instance, the laws of physics are the same here as they are in the Andromeda galaxy. That is a symmetry of location. One proposed yet undiscovered symmetry is called supersymmetry, or SUSY. It postulates that the universe has a hidden parallel set of particles. For every particle we know in the standard model, like electrons and photons, there exists a heavier, unseen superpartner particle, a selectron or a photino. In a perfectly supersymmetric world, the contributions of the regular particles to the vacuum energy would be positive. The contributions from their superpartners would be perfectly negative. The two sets of particles would cancel each other out precisely. The total vacuum energy would be exactly zero. The catastrophic prediction would be tamed, the problem solved by a beautiful deep symmetry. It was a breathtakingly elegant solution. But the universe, it seems, is not so simple. If supersymmetry were a perfect, unbroken symmetry, we should have discovered these superpartner particles by now. We would have found them in our powerful particle accelerators like the Large Hadron Collider. We have found none, not a single one. This means that if supersymmetry does exist, it must be a broken symmetry. The superpartners must be much heavier, much more massive than their standard counterparts, which is why we haven't seen them. But as soon as the symmetry is broken, the perfect cancellation is ruined. The positive and negative contributions no longer balance to zero. While a broken SUSY can drastically reduce the predicted vacuum energy, it doesn't get it anywhere near the tiny value we observe. It solves part of the problem, but leaves a massive discrepancy remaining. The beautiful idea, it seems, is, at best, an incomplete answer. So some physicists have turned to a more radical, and for many more troubling explanation. What if the value of dark energy in our universe is not determined by any fundamental law? What if it's simply an accident of our particular location in a much vaster reality? This is the idea of the multiverse. It suggests that our universe is not unique. Instead, it is just one bubble, one pocket universe in an infinite cosmic foam of other universes. Each of these bubbles could have slightly different laws of physics, different fundamental constants, and in each of these universes, the value of the cosmological constant would be set to a different random value. In the overwhelming majority of these universes, the value would be large. These would be the stillborn universes, the ones that flash into existence and are instantly torn asunder or crushed into nothingness. They would be sterile, chaotic, and utterly devoid of structure or complexity. But in this infinite cosmic lottery, a few universes by pure chance would happen to have a cosmological constant that is incredibly small, close to zero. In these exceptionally rare havens, the cosmic repulsion would be gentle enough to allow the universe to expand slowly, giving gravity enough time to pull matter together to form galaxies, stars, and planets. And on at least one of those planets, intelligent life could evolve to a point where it could build telescopes and ponder the nature of its cosmos. This line of reasoning is called the anthropic principle. It states that we observe the universe to be the way it is because if it were any different, we wouldn't be here to observe it. We find ourselves in a universe with a tiny cosmological constant, for the same reason we find ourselves on a planet with liquid water and a stable orbit. It's a selection effect. We won the cosmic lottery. To many scientists, this feels like giving up. It replaces a problem that could be solved with a deep physical principle with an untestable appeal to infinite chances. We can never visit these other universes, never confirm their existence. Is it still science if your theory can never be falsified? Or is it a necessary, if humbling realization of our place in a reality far grander and stranger than we ever imagined? The debate rages on a philosophical schism at the frontiers of cosmology, but there are other paths to explore ideas that do not require an infinity of other worlds. What if dark energy isn't a constant at all? What if Einstein's lambda is not the final answer? Perhaps dark energy is not a static property of the vacuum, but a dynamic, evolving entity, a new energy field that permeates all of space. This hypothetical field has been given the name quintessence, after the fifth element of the ancient Greeks. Unlike a cosmological constant, the energy density of a quintessence field can change over time and vary from place to place. This opens up a new possibility. Perhaps in the fiery heat of the very early universe, the quintessence field had a huge value, something closer to the natural scale predicted by quantum physics. But as the universe expanded and cooled, this field could have relaxed its energy, draining away over cosmic time, like a ball slowly rolling down a very long, very gentle hill. By today, 13.8 billion years later, it would have settled into the very low energy state that we currently observe. This approach doesn't fully solve the why is it so small problem. It replaces it with the question of why did it evolve this way? Why is the slope of the hill so perfectly shallow to produce the value we see today? But it turns a fine-tuning problem into a problem of cosmic evolution which may one day be solvable. Future telescopes like the Euclid Space Mission and the Nancy Grace Roman Space Telescope are being designed specifically to test this idea. They will map the universe with unprecedented precision. If dark energy is a true cosmological constant, its density should be perfectly uniform throughout all of space and all of time. If it is quintessence, there might be tiny variations, subtle changes in the rate of expansion over cosmic history that these instruments could detect. The search for these variations is one of the great quests of 21st century cosmology. And then there are the truly exotic ideas, whispers from the strange world of quantum gravity, where our very notions of space and time melt away. One of the most profound of these is the holographic principle. Born from the study of black holes, it suggests a shocking possibility that our three-dimensional universe, everything we see and touch, might be a grand illusion, a projection of information stored on a distant two-dimensional surface that surrounds us. It's as if we are characters in a hologram. This idea isn't just a philosophical fancy, it has deep mathematical roots, and it might hold a clue to the dark energy puzzle. The holographic principle places a strict limit on the amount of information and therefore energy that can be contained within any given volume of space. If you try to pack too much energy into a region, it will collapse and form a black hole. When some physicists applied this holographic limit to the energy of the vacuum, they found it dramatically constrained the possible value of the cosmological constant. It didn't perfectly predict the observed value, but it brought the prediction down from 120 orders of magnitude to something far more manageable. It suggests that the very structure of space-time itself forbids the vacuum from having the catastrophic energy that quantum field theory naively predicts. It is a tantalizing, though still speculative hint that a future theory of quantum gravity, one that truly unifies Einstein's world with the quantum realm, will naturally solve this profound paradox. We stand at a unique moment in the history of science. We have created a cosmic inventory, and we have found that we are made of the rarest stuff. The atoms that comprise our bodies, our planet, and our stars account for a mere 5% of the cosmos. The rest is a dark sector, a hidden reality of dark matter and dark energy, whose nature remains a complete enigma. The cosmological constant problem is the most glaring symptom of our ignorance. It is a beacon, a flashing warning light telling us that our current picture of the universe is woefully incomplete. It is the loose thread that, when pulled, may unravel the entire tapestry of modern physics, forcing us to weave a new, more profound understanding of reality. The search for a solution drives us forward. It pushes theorists to dream of new symmetries, extra dimensions, and parallel worlds. It drives experimentalists to build ever more powerful machines to probe the darkness and listen for the universe's secrets. The greatest paradox in the cosmos is not a sign of failure, it is a promise. It is the promise of discovery, the guarantee that there are new laws of nature, new principles of reality waiting to be found. The faint, persistent, accelerating push of dark energy is the whisper of a deeper truth. It is the ghost in the machine of the universe, inviting us to look beyond what we know and to confront the vast, beautiful, and terrifying mystery of our existence. The 120 orders of magnitude do not represent a mistake. They represent an opportunity, perhaps the greatest we have ever had, to finally read the next line in the cosmic story and to understand our place within its grand and unfolding narrative. The journey into that darkness has only just begun.